A game involves spinning a pointer attached to the center of a wheel divided into 8 congruent sectors. These sectors are either blue, red, or green. Chance determines where the pointer will stop. Contestants must bet a certain amount of money to play this game. If the pointer stops on a blue sector, then contestants will receive $28. If the pointer stops on a red sector, the contestants receive $12. If the pointer stops on the green sector, then contestants will lose the money they bet. The game of chance is fair. How much money must contestants bet to play this game? So we're told the game is fair, which means our mathematical expectation will be 0 when we calculate that out. Let's look first of all at the probabilities that we're going to be working with. Since we've got 3 of 8 segments that are red, we know that our probability of red is going to be 3 out of 8. Our probability of blue, there's just 1 segment, so our probability of blue is equal to 1 out of 8. And the probability of green is the remainder, which are these segments here. So our probability of green is 4 out of 8, or 1/2. We're told the game is fair, so our mathematical expectation will be 0. We're also told that if we get blue, it pays out $28. If we get red, it pays out $12. And if we get green, we're going to lose our bet. We start off by defining that the cost to play will be equal to x. Now we want to set up our expectation equation, and it's the probability of each outcome multiplied by the net gain for that outcome. So the probability of red times the net gain, which is 12 minus x, right? Because we have to subtract the cost, what it costs us to play, plus probability of blue times 28 minus x, plus probability of green times negative x. We know that our probability of red is 3 out of 8 times 12 minus x, plus the probability of blue is 1 out of 8 times 28 minus x, plus the probability of green, which is 1/2 times negative x. Now, because the game is fair, that's what we're trying to, we know we're working with a fair game, we're trying to find x, so we can set the expectation to 0 and continue now to solve the equation. The first thing I want to do is get rid of the fractions. It'll make my life easier. So I'm going to multiply everything times 8. Since I can multiply both sides by 8, that'll leave me with 3 times 12 minus x, plus 1 times 28 minus x, plus 8 times 1/2 gives me 4 times negative x. You can do some number crunching here. We end up with 36 minus 3x plus 28 minus x minus 4x, which is equal to 64 minus 8x. Rearranging to move the 8 over to the other side, 8x equals 64. Therefore, x is equal to 8. So in order to have a fair game, the bet should be $8. Question 2. One card is picked from a deck of cards. If a face card is picked, a player can win $25. If a number card is picked, they win $15, and if an ace is picked, they get $50. How much would the player need to play this game if it's a fair game? So again, we'll start off with some basic information. We know there are 52 cards in the deck. We know that there are 12 face cards. We're interested in cards 2 to 10, and we're also interested in the aces. We know that there are 4 aces, and the cards 2 to 10, if we count all of those up, there are 9 cards and 4 suits, so there are 36 cards numbered 2 to 10. So my probability of getting a face card is equal to 12 out of 52, which can be reduced down to 3 out of 13. My probability of getting 2 to 10 is 36 cards out of 52, which we can reduce down to 9 out of 13. And my probability of an ace is equal to 4 out of 52, which we reduce down to 1 out of 13. And if you think about it, this is fairly intuitive. There are 3 face cards in each suit, and there's only 1 ace in each suit, so you can see that it makes sense that you would have 3 face cards out of 13 or 1 out of 13 aces. Now let's look at net gain. For face cards, it says we paid $25, but of course we're going to have to subtract whatever we paid to play. So x is what we're going to pay to play. So the net gain for a face card is 25 minus x. For the cards 2 to 10, the net gain will be 15 minus x, and for an ace, it will be 50 minus x. The game is fair, so expectation will be equal to 0. Let's go ahead now and set up the equation for expectation. We've got the probability of a face card times the net gain, which is 25 minus x, plus the probability of getting 2 to 10 times the net gain, which is 15 minus x, plus the probability of getting an ace times its net gain, and that accounts for all possible outcomes. Substituting in each of the probabilities, now I'm going to set that equal to 0 because my expectation is 0, and I'm going to multiply by 13 to get rid of my fractions. Multiplying that out, we get 75 minus 3x plus 135 minus 9x plus 50 minus x. I collect the like terms together, so I collect the constants together, the 75 and the 135 and the 50, and I end up with 260. And I collect all the x's together, and I end up with negative 13x. Move the 13x over to the other side, and then solve for x by dividing by 13, and we get x is equal to 20. Therefore, the price of the game should be $20 if the game is fair. Question 3. A bag contains 3 colors of candy, red, blue, and green, and a player is asked to pick one candy. The odds of picking a red candy are 7 out of 11. The odds against picking a blue candy are 14 to 4. A player can win $5 if a red candy is picked, double that amount if a blue candy is picked, or they lose their bet if a green candy is picked. What would the bet have to be for this game to be fair? So, the odds of winning red are equal to 7 out of 11. So what that's telling us is there are a ratio of 7 red to every 11 of non-red. Those non-reds could be blue or they could be green. So the probability of getting a red is equal to 7 out of 11 plus 7, which is equal to 7 out of 18. Now, because in odds, the denominator is the number of ways you won't get the desired outcome, in other words, you won't get red, whereas in probability, the denominator is the total number of outcomes. Now, the odds against blue are 14 to 4. The probability of getting blue, therefore, is 4 out of 14 plus 4, or 4 out of 18. Remember, when we got this ratio of 14 to 4, the 4 on the second part of the ratio is the number of blue. Because it's an odds against, that connects to the 4 on the second part, as opposed to the 14. When it's odds 4, then the first number is referring to the desired outcome. When it's odds against, the second number is the number that indicates the successful outcomes. So again, we'll say that x is the cost to play. And now we're going to set up our expectation equation. So 7 out of 18, the probability of getting red. Now we multiply that times the net gain for getting red, which is 5 minus x. Remember, we're told that if you get red, you win $5, but you still have to pay the cost of play, so it's 5 minus x. Then it's plus 4/8 times the net gain for getting blue, which is 10 minus the cost of play of x, plus 7/18 times the cost of play, which is negative x. Now, we need to set this equal to 0, because it's a fair game, so our expectation is 0, and we're going to multiply by 18 to get rid of the fractions. So we end up with 7 times 5 minus x, plus 4 times 10 minus x, plus 7 times minus x, which we can then multiply out to get 35 minus 7x plus 40 minus 4x minus 7x. We can then collect the like terms. We end up with 75 minus 18x. Rearrange that to put the x on the other side. Minus 18x is equal to 75. And when we solve for x, x is equal to 4.17. Therefore, the price of the game should be $4.17 for the game to be fair. Question 4. If you bet $3, you can play a game that involves rolling a fair die. Remember, a fair die just means that it has equal probability of showing up any face. If you roll a 6, you receive $5. If you roll a 4 or a 5, you receive $4. If you roll a 1, 2, or a 3, you lose the $3 you originally bet. This game is not fair. Describe a way of making this game fair. This is definitely a trickier question than what we're used to getting. So first of all, we're going to start off by writing down some of the details. So we know the bet is $3. We've got a 6-sided die, and we roll once. We know that a 6 pays $5, 4 or a 5 pays $4, and 1, 2, or 3 you lose. So the question is, how can we make it fair? think about what things we can actually change which change the outcome or change the expectation of the game. First, let's figure out which way the game is fair or unfair. Is it unfair to the person playing, or is it unfair to the person who's running the game? So let's calculate the expectation as it stands right now. So we want to look at the probability of getting a 6 times its net gain, which is 5 minus 3. The probability of getting a 4 or a 5 times its net gain, which is 4 minus 3, plus the probability of losing times the loss. We can calculate that out. So we end up with a negative 5/6 loss. So on average, we would lose 5/6 of a dollar. To change the expectation, I could either change the payout amount, or I could change the amount of the bet, or I could change which numbers pay for a win. We've already learned in calculating expectation that if we set expectation equal to 0, then we can figure out what the cost to play the game should be. So that's one approach that would solve our problem. We could go ahead and calculate expectation, but not include the $3 price that we were given for playing the game. So we're using essentially the same equation where we take the probability of getting a 6th plus the probability of getting a 4 or 5 plus the loss, the probability of getting the loss times the loss. And then we can set that equal to 0 and then go ahead and solve that. So again, I'm going to multiply by 6 and I'll just solve this quickly. Therefore, if we lower the price to play to $2.17, the game will be fair. There's also an alternative strategy to figuring out how to make the game fair. As we said, we could change the payouts. So let's see what happens if we play with the payout. Now let's say that the payout for rolling a 6 is now $10 instead of $5. That changes our expectation equation. We can see that if we chose $10 as the payout for getting a 6, we would also get a fair game.